Today, we want to revisit our double integral for a sphere in rectangular and polar coordinates, and then maybe start working on some triple integrals for this sphere. We're going to cheat a little bit and use these double integrals as a launching point for our triple integral. But before we do that, I do want to note that we can take pieces of the sphere and we can calculate volumes of parts of the sphere by controlling what we plug into our expression for the volume. Remember, this is over here, this 2 square roots of r squared minus r squared. There we go. This 2 square roots of r squared minus r squared, that is a height. And this r d theta dr is an area. So we're calculating a volume, and the integral from 0 to r and from 0 to 2 pi, those are all the values of r and theta that we're going to plug into the expression for our volume. That's where we're going to calculate the volume. We were very lucky in that this integral will work by doing 2 intervals. The rectangular coordinates also works by doing 2 intervals. It's just that one of our intervals is a variable interval from the negative square root to the positive square root. So what we want to note is that we can find the volume of a part of a sphere by controlling what we plug in to the expression for the volume. So there's certain things that we know, like if I wanted the volume of the top half of the hemisphere, I could just take the total volume that I have, 4/3 pi r cubed, and divide it by 2. And that's all very simple. So I should write a side view. Let me draw a side view as well. Oh, I already messed up. You draw the circle before you draw the axes. So here's our 3/4 view, our top view from the positive z-axis, and our side view from the xy plane, from somewhere in the xy plane. All the pictures look the same because we're dealing with a very symmetric object in this sphere. So let's suppose that we wanted to just take different hemispheres. Let's use this orientation here, where the z is going to be the top and the bottom. It looks like I've set y up as being left and right. And x is the front and the back. So positive x is the front, negative x is the back. Negative y is the left, positive y is the right. positive z is the top, negative z is the bottom. That way we're all standing oriented the same way. Let's suppose I wanted an expression for the volume of the front hemisphere. Now we know that the volume is 2/3 pi r cubed. That's not really the question. It's not really about what the volume is. It's about how we write a double integral to express that volume, in case we need to do something fancy for which we don't have a nice simple expression where we just divide by 2. So the front hemisphere in rectangular coordinates is going to be positive x. So if I want a double integral for the volume of the front hemisphere, where the x's are positive, I'm just going to adjust the values that I plug into my expression for volume. If I just want where the x's are positive, I'll integrate x from 0 to r. If I want the whole front hemisphere, I want all the y's from left to right, so I'll keep all the y's. And I want that whole front hemisphere, so I want all the z's from the bottom to the top. So I just still want the 2 square root of r squared minus x squared minus y squared. And we're still got a double integral dy dx. That's no problem. We said I want the front hemisphere. The front we just said was the positive x and is the positive x. So we just have to write down where positive x is. We still want plus and minus y. We still want plus and minus z. Now, this is what we would write if we were writing a double integral in rectangular coordinates. But we have 2 coordinate systems now, and we have to understand them both. So we should be able to write the front hemisphere, a double integral for the front hemisphere in polar coordinates as well. So if we think about where x is positive, we still want the y's to be negative and positive. So if we look at our top view, I want x's to be positive. I still want the y's to be positive and negative. I want both y's. And I still want the z's above and below the xy plane. So if I want the front hemisphere, I still want 0 from r equals 0 to r equals capital R. I still want all of these r values. So I'm going to control the front hemisphere where x is positive by plugging in the right values of theta. So I'm going to adjust my values of theta to go from negative pi over 2 to pi over 2. And that will give us the front half of our hemisphere. So I can adjust my original integral. I still want r to go from 0 all the way out to the edge. Where I'm going to make my adjustments is in the values of theta that we use. I still want the top and the bottom, so still 2 times the square root of r squared minus r squared. This is still an integral in polar coordinates, so I need r d theta dr. But I'm going to use my values of theta to be where the x's are positive. So I want the fourth and the first quadrant. So I'll adjust my values of theta to get the quadrant 1 and quadrant 4. So in these polar coordinates, I can adjust my value of theta to grab just quadrant 1 and quadrant 4. In rectangular coordinates, we adjusted our x values to grab quadrant 1 and quadrant 4. So our original double integrals described the entire sphere, the front and the back, the left and the right, the top and the bottom. I don't know why the y's, I list the negative ones first, but for x's and z's, I list the positive one first. I should be like all front and back, right and left, top and bottom. Now I'm going in the right order, or the same order. But it's weird to say from right to left instead of from left to right. All 6 parts. And then I can take parts off. I can take parts off by adjusting the values that we plug in. In the case of these double integrals, I don't have to adjust the expression unless I want to mess with the top and the bottom. So for example, let's suppose I didn't want just a hemisphere. I'm going to grab the hemisphere on the right and under the XY plane. I want the right hemisphere, and I want this to be under the XY plane. So by asking for the right hemisphere, I want the y values to be positive. So this right hemisphere says y is positive. And this under the XY plane, all this is telling me I want z to be negative. Since I want to make some adjustments to the values of z that I want, I'm going to have to mess with my expression because I had a double integral and I used z as the height and the dx and the dy as the area, or the r d theta dr as the area. So I have made a request that my height I made an adjustment to my height. So that means I'm going to have to mess with my expression. Fortunately for our heroes, I just went with z is the negative part. So that part we're just going to get to cut in half. And so instead of having the positive square root minus a negative square root, I just want 0 minus the negative square root. I don't want 2 of these square roots. I just want 1 of them. So that's going to cut my z's in half and just give me the bottom volume. To get my right hemisphere, I want my y's to be positive, but I'm going back to all my x values. So my right hemisphere is where y is positive, and I want all the x values because I want that hemisphere, but I want to cut that in half. Quarter sphere? I don't know. So I want to go back to all my x values. Because the quadrants that I want are where y is positive. That's quadrants 1 and 2. I want quadrants 1 and 2 because those are the quadrants where y is positive. So the x's are negative r to r. But I only want the y to be positive. So I'm going to start my y's off at 0 and go up to the positive square root. Since quadrant 1 and quadrant 2 are where y is positive. Since I'm only asking for under the xy plane, I want z to be negative. So instead of 2 square roots of r squared minus x squared minus y squared, I only want 1 of those. Remember that 2 came from subtracting a negative from a negative, or the negative, subtracting a negative. So we're adjusting our z values to choose below the xy plane. This is still a double integral in the same order, dy dx. X going from negative r to r gives us everything from front to back, or from back to front, since we list from bottom to top. Y going from 0 to positive square root is going to give us everything from 0 to the right, where y is positive. That's quadrants 1 and quadrants 2. And then just using 1 square root of r squared minus x squared minus y squared is going to give us the bottom half. Note that this is the same value if we did the square root of r squared minus x, r squared minus x squared minus y squared minus 0 for the top half, but that's because those two are going to be the same volumes. The volume down below is the same as the volume up above because of the symmetry. Any questions? How's everybody okay? In the polar integral for the right hemisphere under the xy plane, we're going to do the same adjustment to z to choose below the xy plane. And we're going to get quadrants 1 and quadrants 2 with the value by controlling the values of theta. So this one's going to have to look like I didn't really give myself enough space. So I can make the same adjustment to get z to choose below the xy plane. So I just need one of these square roots of r squared minus little r squared. This is still a double integral in polar coordinates, so I still need r times d theta to make a length. And a dr. Now in this case, I want where y is positive. So if I go back to my picture, I still want all the r values from 0 to capital R, all the way around. 0 to r, 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 all the way through. So my r is still going to go from 0 to r. My theta, I want to choose the first two quadrants. So I'm going to start theta at 0 and get the first quadrant 1 and quadrant 2 by going from 0 to pi on theta. So here we are just adjusting z to choose the part of the hemisphere, adjusting z to choose the part of the sphere that's below the xy plane. We adjust theta to choose quadrants 1 and quadrant 2. I didn't have room to write my note down here, so I had to write a warp in that hole and out this one. I had to time it correctly because there's going to be that plant with the teeth like coming out of there eventually. So you got to use the warp when the plant is not going to come out and eat you. You know what I'm talking about? Has everybody played Super Mario World? If not, that will be your homework. Find a Super Nintendo. Play it's no, I'm just kidding. That'd be ridiculous. I would never assign that because it's a platformer and I am historically bad at platformers. There's just like, I don't know what is wrong with the way that my brain interacts with my eyes and my hands that I cannot do that. Like if there's different sized jumps, like Tomb Raider style, that's different. Because there's a kind of a set number of jumps. Stand, jump, running jump, stand, jump, grab, running, jump, grab. And you can just kind of like look and see, oh, that's definitely a run, jump, grab, right? You can tell by looking at it. But with platformers where Mario can jump up and you can control how far he goes, I'm never going to land it. And the first time it shows up, it's like, oh, you have to jump and there's like a moving platform. No, I'm never going to hit that. That's just the end of the game for me. They're like, oh, did you finish Super Mario World? I'm like, oh, yeah, totally. Wow, what did you think of that one level? Didn't get there because the game ends for me the first time I have to jump on something that's only 1 square wide and it's moving. Like, oh, that's one of your basic platforming skills. I'm like, oh, yeah, and I don't have it. Which is a different lack of video game skill than my first-person shooter style or any kind of shooter style, where my reflexes are just trash. And I'm like, oh, look, there's oh, I'm dead. Like if it's another human controlling the person shooting at me, I'm just dead. Because there's something about like gamers that are like, oh, something moving, and they just instantly aim and shoot it. And I'm like, oh, look, there's an enemy. I think, oh, I'm dead. Then I respawn. So I go, okay, where was that guy? All right, he's over here. There he is. And I'm dead again. See, that's this. There's certain video gaming skills that I just don't have. There are other video game skills that I have in abundance. Like if it's, you don't really have to improvise, you just have to do the same thing over and over again, like World of Warcraft, non-PvP, no problem. It's just like the same sequence of buttons, like all the time. I barely had to pay attention. That comes from my early video gaming experience in the 80s in arcades, where all video games are pretty much the same thing over and over again. So there was a game called Tempest. It was a vector graphics game. That's a game that you have never heard of, and a style of video game you probably have never heard of. And I could not be stopped on that game. If we were going to go to the arcade for 3 hours, I needed 1/4. If we were going to go to the arcade for 6 hours, I needed 1/4. So I put it in a Tempest and just tie up that machine. My other friends are like getting more quarters and playing other games. I'll just play the one game for multiple hours. You know what I mean? Anyway. What is it? Oh, that's right. I had to build a warp. So we adjust theta to grab quadrants 1 and quadrants 2, but I still want everything. R goes from 1 to 2. How's everybody okay? Let's suppose that we want the volume of a spherical shell with an outer radius of 5 and an inner radius of 3. That is, the shell is 2 units thick. Once again, the point is not actually finding the volume, because I could just take the volume of a sphere with a radius 5, pi, 4/3 pi times 5 cubed, and subtract the volume of a sphere with a radius of 3. So 4/3 pi times 5 cubed minus 4/3 pi times 3 cubed. And that'll give us the leftover, the shell that's 2 units thick. So finding the volume is not the point. So the volume that we're looking for would just be 4/3 pi times 5 cubed minus 4/3 pi times 3 cubed. Finding the volume isn't the point. choosing the appropriate tool at hand to find the volume and writing a double integral for it, that's the point. I made these two circles almost perfectly too small for me to write inside them, because it was really difficult to write the r equals 3 and the r equals 0 in there. But it was big enough that I attempted it. So, but perfectly too small. In this scenario, polar coordinates are going to be awesome. Rectangular coordinates are going to be a nightmare. So polar coordinates are going to work out perfect for this. Polar coordinates will be good for this. Rectangular coordinates will be trash for this. Rectangular coordinates is going to be so bad, I should have written the trash in all caps, but it's going to underline it 3 times. Just be excessive, like 12 exclamation points. In polar coordinates, we can see exactly why the polar coordinates are going to be awesome. Because I want to go all the way around, I only want the values of r between 3 and 5. So this circle is 2 intervals in polar coordinates. Theta goes from 0 to 2 pi to go all the way around, and r goes from 3 to 5. Perfect. No problem. So for polar coordinates, everything is awesome again. I just want this 2 square roots of r squared minus r squared, just like before. Because I want the bottom and the top. This is still a double integral in polar coordinates, so I need r to turn d theta into a length, and I still want theta to go all the way around. Nice. And then there's the dr. We're going to control how much a sphere we have by adjusting the values of r. I just want the values of r to go from 3 to 5. That'll give me that outer shell. if we try to break this up in rectangular coordinates, I have to say what's x between and what's y between. And what's x between and what's y between changes depending on where we're looking. So there's a what's x between. I think I need another one. So if I think about what's x between, I can't just do the x's from -5 to 5. Because I don't want all these x's in the middle. So already, just because these x's, I've got two integrals that I'm going to have to deal with. X goes from -5 to -3, then I have a whole separate one from 3 to 5. Oh, but hang on. I do want this stuff down here. So I do want the x's from -3 to 3, but my y's change in there. So in this section here, y goes from the negative square roots to the positive square roots. So in this section, y goes from negative square roots to positive square roots. That's from x equals -5 to -3. But then between x equals -3 and 3, now I have two integrals again. Y goes from the negative square roots. Oh, I should be more specific, because we have two different circles running around. Oh, I forgot. It just keeps getting worse. This is the negative square root of 25 minus x squared to positive square root of 25 minus x squared. And then in the section from 3 to 5, we also have the negative square root to the positive square roots. And the only circle that we're dealing with is the outside one. So here, we've also got y from negative square root of 25 minus x squared to positive square roots of 25 minus x squared. But in this middle section, we've got kind of a mess. Now we're going y from from positive, let's look at the top half. To get this top half up here, in that section, y goes from, on the bottom, the radius 3 circle, to the radius 5 circle. That's the top parts. We've also got to grab the bottom parts. This simple washer shape, which was just an interval for r, is 4 integrals in rectangular coordinates. This right piece, the left piece, the top section, and the bottom section. 4 integrals just to deal with those 4 pieces. Any questions? Polar coordinates, good for this. We don't have time to do an example of where polar coordinates are really bad, but if you build a rectangle, x goes from 0 to 5 and y goes from 0 to 3. That's kind of a pain in the butt to draw in the polar coordinates. Any questions? Comments? Snide remarks? At least all the way around this ring, z still goes from the bottom to the top. That's still in play. Any questions? Comments? Snide remarks? Oh wait, we've got a giant hole. I just realized. It's not 4. I just realized we still actually do need, I was wrong. We're gonna need more integrals for that stuff inside. And there's gonna be 2 of them, one for the bottom and one for the top. At least the x's and y's are easy to deal with in that one. All right. So the point is we have to know both because we have to choose which one is best. Not only do we have to have both tools in the toolbox, we have to know how to use both tools in the toolbox. All right, tomorrow we're going to look at this, change this double integral, trade it in for a triple. Actually, no, tomorrow is a flex day. So I'm here and y'all are not, right? Tomorrow the 12th, October 12th is the flex day. Check your calendar in case I'm wrong. Usually students know when things like that happen. You instinctively know Columbus Day or Indigenous People Day, not a holiday. Martin Luther King is a holiday, so you know where the holidays are. But you might not know flex days. Tomorrow's, I think, is a flex day. So no class. All right, so on Thursday, we'll set up a triple integral for this and do the same kind of thing. How do we get pieces of this described with a triple integral? That's it for today. I'll see y'all on tomorrow. Everybody on Thursday. Everybody have a good couple of days. And thanks for playing.